I would like to start today's lecture on a different topic, which is telling you about the peer evaluation required. Actually, now before I do that, I'm not sure if all your tutors spoke to you about what's necessary, hang on, for the project presentations. Have you been told what's necessary? No, okay. So, well, when I say what's necessary, what we would like to see from you. So you have been, oh, I hope I can, have I got it here? Actually, in the break I'll look for it and we'll talk then. Okay, we'll talk about it in the break. Okay, for now, I want to talk to you about the fact that you are going to be evaluating each other in the project. Which people that are doing most of the work are going, yay, because I did most of the work. And for people that went, oh, come on, we all did the same amount of work, you're going, oh, God, do we have to do this? So, yes, you do have to do it. And this year, for the first time, we're trying out this package called CATME, which is a peer evaluation tool. And it stands for Comprehensive Assessment of Team Member Effectiveness. And we're going to assess your individual presentation, your individual contributions to the project. So you're going to get an overall project mark, and then based on these surveys, you'll then get allocated a percentage of that. So if you all manage to mark each other evenly, you will of course all get the same mark. Okay? So that your peer and self ratings have reliability and validity, when you go in, I will be sending you an email. No, I won't be sending you an email. I will be starting the survey on Monday morning, and you will receive an email from CATME saying there's a survey for you to do. Now, as part of doing that survey, it will require you to log in and come up with a password. So the password you put in automatically becomes your password. You'll go in there, and the first thing you'll do is you'll be asked to do a calibration survey. So there's an existing survey in there already where, and it looks a bit like this, where you'll first of all be told about 4 people. You'll be told a little bit about them, how much they contribute, you know, how good they are at contributing to the technical side or just to the motivation side. And then you'll be asked these certain questions. And these are the questions you'll be answering in your survey. So when you come and see your survey, to do your survey, you'll see your names up here on the screen. And there'll be 3 of you typically. Now, the questions... So by doing the survey, that will give you an idea of how you're meant to be, well, what the questions are. So you'll get an opportunity to look at the survey before you complete one. Now, as part of these surveys, there are 5 questions you are going to actually give an answer to, or will click on a dot for. And they relate to, if you look at the top up here, contribution, interacting with teammates, keeping the team on track, expecting quality, and having relating knowledge, skills and abilities. So you have to evaluate yourself as well as your teammates. So you have a choice of 5 dot points in here, and you can have a read. At the very top end of the scale, you do more work. You do more or higher quality work than expected. You make important contributions. You help teammates who are having difficulty. That's the top end of the scale. And then at the very bottom end, unfortunately, hopefully none of you are this person. You don't do your fair share of the teamwork. You miss deadlines, and you don't assist teammates. So you have this possible 5 bullet points or dot points you can actually choose. So you have to rate yourself, oops, because this isn't the real survey, you put a click on the dots, relative dots, next to the name of the person, okay? So that is based on contribution, and then etc. It goes in and has questions relating to teammates. Of course, this blank in between is where you place the person or yourself halfway between. So you answer those 5 things, it then comes back to us, and then you'll complete it. And then when the whole thing is finished, you'll then get a notice back, an email back from CATME, and it will tell you the results of your survey. So you will then see how the group was rated on average and how you were particularly rated. So we'll see if you are rated higher or lower at particular skills. So this is meant to be feedback for you. So you may do really well on having related knowledge skills, but you may be doing very poorly on keeping the team on track. So this is about your team effort to the project. So expect the email. Complete. I'll send you an email as well telling you what time limit you have to complete the survey. I'll set it going on Monday and I'll have it running until probably the following Tuesday or Wednesday. So it will be going for about a week and a couple of days. Now after about a week, people that haven't completed, I can then send a reminder to apparently again by pressing a button. I haven't done this before. So you'll get a reminder again. If you choose not to complete the survey, you will get a mark based on your team member's assessment of you. So it's to your advantage to actually fill out the survey as well. But we're not going to wait for you, so you're not going to email me a day after it closes and say, oh, sorry, can I please fill it in now? There's a time limit. You have to fill it in within the time limit. Now, I should probably talk all the recordings off. If you decide that you are happy that everyone has contributed to the same amount to this survey, what you need to do is you need to agree on which of these even points you're going. If you click on everyone the same, okay, you'll get the same mark. But you either have to all click on the top level or all on the middle level. You can't have one person clicking all on the middle level and one all on the top level, because then you will get slightly different values. So what I'm telling you is if you're happy that you want everyone to get the same mark, do have a read. It's probably best if you do fill it out honestly, because the purpose of this is to provide feedback to your partners to ensure that they know what they're not good at and to try and improve what they're not good at. Okay? Okay, so expect that, fill it in, and then you'll see the results of it. I won't talk about the project yet. We'll go back and we'll start on the actual course material. Okay, so we're back with our bending moment diagrams, and I gave you some, you don't call it homework, do you, anymore? I gave you some work at home. Something to challenge you at home to do. We finished up having completed the bending moment diagram where we had a moment, there's a cantilever simply supported beam with a point loader moment. And the contribution of the point load ensured, well, turns out the bending moment, when we drew it, was all above the line. And because we draw our bending moment on the side of the beam in tension, that meant from that we could then say what our deflected shape looked like, and we drew our deflected shape as having tension on the top throughout, because our bending moment told us that. If we had attempted to draw our deflected shape before, we may have been tempted to have drawn something that looked like that, because we see this moment applied. So sometimes it's worthwhile drawing the deflected shape first, and sometimes it's worthwhile waiting, getting the bending moment right, and then having a sketch of your deflected shape. In this instance, I wouldn't have attempted the deflected shape first. I would have waited till I'd drawn my bending moment. Let me just take that bit off so it doesn't confuse anyone. Okay. So this is the work at home I gave you to do. Did anyone do it? Just lie to me. All put your hands up. Did anyone do it? Fantastic, everyone. Okay. Hopefully some of you did. It's to your advantage to do these questions. I left you with having given you the reactions and having drawn the shear force diagram. So looking at the shear force diagram now and utilising this wonderful relationship between shear and bending, when we come to draw our bending moment diagram, what are our rules? Well, we mark where our bending moment is known to be 0, and it's known to be 0 at the pin end support, at the cantilever end. Our beam runs continuous over our roller, so that means there's curvature in it, there's bending in it. So we have two known values of our bending moment. Then we look at our shear force diagram, and we know as well as this representing the shear force diagram, it's also equal to dm dx. So this is telling us our bending moment diagram has a constant slope of 20 between the two loads, and then it has a constant slope of 80. They're both positive values, which is normally an upward slope, remember, but because we draw bending moment positive down, that means a positive value actually equates to downward slopes in our bending moment diagram. So again, joining the dots, we know our bending moment is 0 at the cantilever end, and it has a slope of 80, so that means it's a linear line with a slope of 80. When I come and draw my other line now from the left support, because my slope is 20, I'll just automatically draw it less slopey. Now, again, I'm a bit confused as to what to do with the bending moment, applied bending moment, but I know it affects my diagram. So I'll just take my sloping line, I'll call it the gradient, and I'll just take it up to that moment value. Now, the other way to look at this is, how did I get that linear line there? I can cut the beam. Consider I have a load applied on it. Say I've cut it a distance x, put my moment in, take moments at the cut, and say, well, there you go. I have minus m minus 80x. My bending moment is equal to minus 80x, which, of course, is the mathematical expression for that line. So you can do it either fully graphically or mathematically if you want. Now, based on the other problem, I said if you just remember that an anti-clockwise moment gives you an upwards, and I should draw it all the way up, a step up in my bending moment diagram. How far up do I draw it? This is where I can put some values in, because what is the moment down here? It would be the area under here, because moment is also equal to the integral of your shear force, so it's also the area under it. Or I can just consider the moment at the load here to be 20 times 4, so that value in there is 80, and thus the value up here would be 80 times 8, which is 640. Now, when I have this step up in my bending moment diagram, it's stepping up a total of 800 Newton metres. Thus, it's taking me to a value of, and because I've written that there, I'll just move that across. So it takes us up to a value of 720. And I'll write over here gradient, again, equals 20. And my shear force is constant again, which means it then continues to slope down. And there is my bending moment diagram this time. So based on the bending moment diagram, we can now have an attempt to sketch our deflected shape. And we draw our bending moment on the side of the beam that's stretching in tension. So according to this, the top of our beam is stretching, but right of the pin support, we have the bottom of our beam in tension. So we know we have tension at the bottom of the beam and tension at the top of the beam. So this time when we attempt to sketch our deflected shape, you don't know how much it moves up and down. We're going to learn how to calculate deflections to do that. So whenever you're asked to draw the deflected shape, you're asked to sketch it, which means just give us some idea of what you think it looks like. So I would say I've got tension on the bottom and I have to have a point of inflection here. Oops, so I'm not doing a good job of this. How does that look to you? Pretty crap. Okay, so there's a point of inflection here, because a point of inflection corresponds to where our moment passes through 0. And that would be my attempt, I'd draw it a bit nicer than that if it was on the test, at the deflected shape. Now, people asked me yesterday, with the moment applied anti-clockwise, I would expect it to be a step down. The way I think of a moment, I think if I have a moment applied that way, just on a simply supported beam, my beam would be deflecting like so. So thus, in terms of my bending moment diagram, my bending moment diagram would be down here, and then it has to come up, so it must be a step up. You can remember it however you wish, just draw it such that anti-clockwise is a step up. Okay, now I want to introduce you to the principle of superposition that some of you may already know about, because what I want to do is I want to break down these bending moment diagrams we've drawn here so you can make a bit more sense of them. So have you met the principle of superposition before? Some of you have, some of you haven't, some of you don't know what I mean. But if I say I have my pen here because I forgot to bring my flexible ruler, and I push down with a kilo and it deflects down 1 mil, if I push down with 2 kilos, how much is it going to deflect down? 2 mil. Okay? That's using the principle of superposition. The effects of each load can be calculated separately and then added together to obtain the effect of all the loads applied together. So this principle only is applicable to elastic behaviour, linear elastic behaviour. So if I say I press with 1 kilo, it moves down 1 mil, and I say to you, how much will it move if I press down with 10 kilos? You say 10 mil. That's in the linear elastic range. So we can work things out separately and add them together. So I want us to go back to those 2 previous examples we did of the moment and the point load, and just to look at the effects of those 2 loads separately. So here our moment was 800 Newton metre, and so we can relate this to 2 problems. I'll run through the 200 Newton load first and then the 80 Newton load. So let's have a look. We have a moment applied here. So can you imagine what this deflected shape to the right will look like? Well, I drew it on the previous page. If you can't imagine, it would be so good if you did buy some sort of flexible ruler. You can stick things on your pens in the exam and push down on it, and no one's going to accuse you of cheating. Just say, Lizzie said it was okay. So by all means, do whatever helps you. With this deflected shape, it's fixed here, it's fixed at the 2 supports, well, it can't move, and I'm rotating it down. So I am, in fact, and I'm not drawing this very well at all, I'm getting that shape. Now, this bit here, beyond the support, is straight. It's only moving down because at the support it's been rotated around. So that would be my deflected shape there. Now that's such a bad deflected shape. Let's just take away that bit there. So hopefully you can all see that deflected shape. So my shear force diagram there, based on that quite ugly deflected shape I drew for you, if I took this pin support away, which way would the beam want to flip? Up or down? Down. Therefore we know our reaction here will be upwards because it's not flipping down. And if I let go of this support, this roller support here, which way would it want to move? It would flip up. So the reaction here must be down. And in order to get forces in the y direction equal to 0, you know those 2 forces are equal and opposite. They are a couple opposing the moment. The moment's trying to rotate it one way, and these 2 forces are stopping it. I've got to make sure my arms are going the right way. So shear force diagram, I step up, I move across, and I come down. This is a moment, it doesn't affect the shear force diagram. So my bending moment diagram now. What's it look like? Can you imagine? We know it's 0 here, and this time we know it's 0 all the way along here, don't we? There's no action in there. The beam is straight, moment is proportional to curvature, there's no moment here. So we have a 0 moment up till here. Now, we have a constant positive slope because our shear force is constant and positive. Therefore, we have a sloping down bending moment diagram. So based on it being 0 at the left, it slopes down. Based on it being 0 at the right, it has to slope up. So there is my bending moment diagram. Make sense? Kind of? Think about it. Okay, now we have our point load. Now we apply a point load. How is this thing going to deflect? Do this for me in the air so I can see you're awake. Sorry, did someone do that? How's it going to deflect? You all doing that for me? Wake you up. Come on, everyone. How's it going to deflect? Okay. The deflection has to be 0 here. Sorry, I have to keep myself awake. It will deflect down like that. If you can't see that, buy that bit of flexible moulding from Bunnings. Get someone who you live with, your brother, sister, mum, dad, flatmate, to hold the ends and push down and see what it does. So, tell me now, at this roller support, if we take this roller support away, which way will it want to move? Down. So this reaction must be up. And if I take the pin support away, which way does it want to move? Up. So we know that this reaction is down. So without doing any calculations, we have an idea of what direction. So drawing now the shear force diagram, it will look like so. A negative is an upward slope, a positive is a downward slope. Our shear force is constant, our bending moment is therefore linear. Bending moment here is 0. At the pin support, bending moment at the cantilever is 0. Draw the bending moment diagram. I've basically told you everything, and it's just a question now of joining the dots. Yep, good, I'm seeing that and that. Beautiful. So, if I do now just put some values, if I just do this when it was 200, will give me the big, okay, in black, and the value in black. If I now, I'm just going to move across to green. That wasn't green, that was blue, wasn't it? When we had 80 on, our shear force, all our forces will be smaller. And can you imagine our bending moment diagram would also be smaller? So if I combine those two bending moment diagrams, can you see they combine in different ways? If that force here is 200, have a look. I have this, see this zigzag happening in here? So that zigzag action is a result of the bending moment caused by the applied moment. And this popping up here is a result of the point load. So in the previous example, we got two different bending moment diagrams. When our load was 80, this value in here was 640, that value in there was 720, and that value in there was 80. However, when the load was 200, that value up there became 1600, that value became 1200, and it didn't pop down, it was 400. So I just want you to realise that those two previous problems I gave you, in effect, had the same basic, the same breakdown, okay, the same bending moment diagrams to superimpose, but because their values were different, they came out looking differently. And as such, when you look at these combined deflected shapes here, when you had the 200 load applied, it was simply popping up because the 200 was so big. But when that became 80, then the effect of the moment was enough to actually bring it down. Yep, good. Moving on. That was just horizontal beams. And I know you find horizontal beams really boring. So we're going to go into bigger and better things, looking at crank beams now. Because, of course, most of what we see, buildings we see, okay, are not in one straight line. They're made up of columns and beams. So with crank beams, we're saying now the connection between the members is rigid. When it comes to your trusses, all those joints in your trusses, people are asking me, are pin joints. So the effective length of all your members in your truss is 1 because the two joints are assumed to be pinned everywhere. Now we're dealing with systems, where we have rigid connections everywhere. And I forgot to bring the model because it was raining. I'll bring it next week. I have a bit of plastic moulding, an L-shaped bit of moulding. And when you have a rigid corner, and you apply a load to it, the corner either rotates two ways. It's either what I call an inwards corner or an outwards corner. So you don't have a corner, hang on, that does this. So in this case here, can you see I've got tension on that side and tension on that side? And to cause tension on the outside here of the vertical face, the moment would be anti-clockwise. And to cause tension on the bottom face of the horizontal beam, the moment would be anti-clockwise. And if you consider that corner as a free body diagram, can you see it's not in equilibrium? So no corners will have one side inner and one side outer. So it's always true, apart from where you have moments applied on the corner, which I won't do to you. A corner has either tension on the outside of the two members or tension on the inside of the two members. And this will help you draw your bending moment diagrams. So, as I said here, it's not possible to have that sort of shape in there for your corner rotation because you don't get moment equilibrium. So that's enough knowledge for us now to attempt to draw our bending moment and our shear force diagrams. So, as with the previous problem, before we attempt to do it, let's see what our supports and reactions are doing. Now going around a corner to start off with can be quite difficult. So what I've done here is I've cut a free body diagram here and I've considered the two systems separately. So when we look at the horizontal member here, we have a load down, so this vertical reaction here must be up. When you look at horizontal equilibrium, there's no load on the system, so there must be no load in the horizontal direction. Those two forces as drawn, however, create a couple. So the moment I have, the internal moment I have in the beam here, is it clockwise or anti-clockwise? To give me equilibrium. So I'm expecting you all to be going, okay, that's going clockwise. So to oppose that, the internal bending moment here must be anti-clockwise. Now, remember I told you about sign convention. If I draw it anti-clockwise on one side, I draw it clockwise on the other. So when you put it together, it's in equilibrium. If I have drawn my moment here now, anti-clockwise, that means the moment on my vertical leg will be clockwise. My force here I have drawn up, so the force here must be down, and therefore my reaction support would be up, and the moment down here would oppose it. Is everyone happy with that? So now we can draw our shear force and bending moment diagrams. So looking at this horizontal face here, okay, you start at the left-hand side and you follow the load. So our reaction says it goes up, moves across, and then steps down. So there's the shear force in the horizontal part of my crank bent beam. Now when I draw shear force, up till now I've said shear force is vertical force. But to be more exact, shear force is the force perpendicular to the beam you're considering. So now when we look at this vertical face, shear force would be the horizontal forces. When you look now, you have to define what side you're looking at it from. So what we do is we draw a little eye, and I can rotate my computer around now, but it won't help the screen up there. But if you do look at it sideways anyway, there's no force in this direction. There was no reaction, so therefore I have no shear force in that part of the beam. So knowing our relationship now, shear force is equal to dm dx. I have a positive shear force. That equates to a downward slope. I have no shear force in here. So the easiest way to look at the vertical leg is to actually rotate your pages round and pretend it's horizontal. So we'll tackle the horizontal leg first because that's always the easiest. What's the moment at the end of a cantilever? 0. Our shear force is constant, so our bending moment will be linear, so it must be coming up like so. Now when we do go around a corner, we usually just close it up, but you don't have to, but you close it up. You draw the line down. Now coming back here, I've drawn my bending moment above. Can you imagine how this thing deflects? It's very important that you can imagine. This thing would deflect down like so. So this is what I would call an inner corner. I have tension on the outside, and therefore I must have tension on the outside of the vertical face. So going around the corner, this value of tension, of bending, must equal that value of bending. If you open this up and flatten it out, it's currently an L shape. If you actually lift up that horizontal leg and draw it straight, you'll see that these two members here should join up. So going around a corner, the moment in one leg always equals the moment in the other leg. So I do have a moment in here. I have one because I can see I've got that vertical leg curving. But according to my shear force is 0. So if my shear force is 0, that's telling me the slope of my bending moment is 0. It's not telling me the value of the bending moment is 0, it's telling me the slope is 0. So there you go. That means my bending moment in here will be constant. V is equal to dm dx. If V is equal to 0, dm dx is equal to 0. The slope of that line there is 0. So there's my bending moment diagram. I would like you now to attempt the same thing on a similar bent beam, this time with a horizontal force applied to it. And I'll just look for that thing I was looking for. Oh, I thought that was locked. I froze that. Sorry. So if you don't want to break it up into two free body diagrams, you don't necessarily have to. So let's first work out what direction the reactions are in. Is there a horizontal reaction? There must be, because there's a horizontal force applied. So there's a horizontal reaction here. Is there a vertical reaction? This is like that survey thing I did in week 3 where you all got it wrong, except 5% of you. Vertical reaction here, there's no vertical load acting, so that must be 0. Now can you see those two forces as drawn are creating a couple? And that couple's rotating anti-clockwise. So to oppose that, my moment here must be going clockwise. I can draw it up here now as two free body diagrams. The force is to the left. If I draw my unknown shear, axial and moment, I'll have no shear in this free body diagram system, no moment, just a horizontal. Now when I draw, remember at an internal pin, when its force is in one direction, you draw it equal and opposite. That means I would draw that force in that to the left. And when I consider my vertical free body diagram, that means I must have a force to the right. And again, those two forces are creating a couple going anti-clockwise. So that moment must go clockwise. So when you draw your shear force diagram, Imagine you're looking at it from that side. If you choose to look at it another way, as long as you draw your eye on, you won't get marked wrong. So is there any shear force in this horizontal leg? No, it's only axial force. So with respect to the vertical leg, you start at the left-hand end. Based on my eye, the left-hand side would be the bottom bit, and I step down, and then I move across, and there is a force to the left because that's my load. So I have equilibrium. So I have a zero shear here. B is equal to dm dx. So that's not necessarily, as I said, telling me my moment is zero. It's just telling me the slope of my bending moment is zero. However, if you do look at this free body diagram here, geez, that freaked me out. I leaned forward on these buttons here, and I didn't know, and I leaned forward and this thing started moving. Anyway, so, okay. Is there any bending moment in this horizontal leg? No. Okay. Can you imagine how this thing deflects now? It's off the screen, so I won't draw it deflecting too much. And I'm exaggerating. This bit here should be straight. And it's just tilting up because this thing is bending. So the corner has to remain at 90 degrees. So my bending moment, what side have I got tension on? The right side. According to my shear force diagram, it's a negative shear force diagram. Sorry, I'm freaking out now. Which way is my force going? It's a negative shear force diagram, so that's an upward slope. So my bending moment diagram will look like that. Does that make sense? Then you go and check it. I got bending on that side. Yes, that's the side in tension. My horizontal leg is straight. Yes, there's no bending moment in it. Because a negative shear force is an upward slope, but going round a corner here, because I had no moment in my horizontal leg, that meant I have to have no moment in my vertical leg. So going around a corner, the moment was zero. And what did I say about a fixed support? The moment in the beam will have the same magnitude as the reaction moment. So that reaction moment, the moment in the beam is equal and opposite, but it has the same magnitude as the reaction moment. People get that? You'll have plenty of practice in the problem set classes. Third one. Shear force diagram, bending moment diagram. Breaking it up into two free body diagrams. When I break it up, of course, when I cut a beam, I have an unknown shear, axial and moment. So looking at this system here, I have a moment applied, therefore I must have a reaction moment equal and opposite. There's no vertical force, there's no horizontal force, so the only internal action there is a moment. So therefore the moment here I would draw as equal and opposite on the other side of my cut, and therefore that reaction moment must be anti-clockwise, which it would be to oppose the clockwise. Deflected shape. Yep, good. That's meant to have tension up here and tension to that side. That moment is bending it. So I know which sides I have tension on. It's curving. I know there's moment in the beam. When I come and draw my shear force diagram, are there any forces at all acting on this system? No. So my shear force is zero. This is a case of pure bending. By pure bending, we mean there's no shear anywhere. So, once again, our shear force is 0. That's telling us the slope of our bending moment is 0, but it's not telling us our moment is necessarily 0. And we know it's not 0 because we can see our beam is curving. Bending moment diagram. Yeah. I'm seeing some fingers go up. Constant, going round a corner. That value must equal that value. So you can see going around a corner here, those corner values equal. Going around a corner here, they're both 0. And going around a corner here, they're both equal. So when your bending moment, with an applied moment like so, your bending moments are both on the outside. If I have that same frame and I now apply a bending moment in the opposite direction, my bending moment diagram this time will be on the inside, and they'll overlap. But that value will be equal to that value. So your bending moments are either both on the inside or both on the outside. And they have the same absolute value. Okay, I think I'll tell you about Project 2 now, as your interesting break. Do you need a 1-minute break? Do you just notice how they're getting shorter, 5 minutes? Do you need a 1-minute break now? Do you want a break now? A time break? Talk to me. You're just taking the time break. You're not telling me what you want. Okay, if you want a time break, what I'll do is I'll give you a time break. And I will leave that one up there for people to get going on that bending shear force diagram. And this can be a project question break as well for people that want to come down.
When I was doing my member calculations for the truss, when I went across from one side, it all made sense. I got to the middle. When I went past the middle, I started getting things that should have been intention being expressed, not on the top and the bottom, but in the middle members. And I realised if I started from the other side, I would have had exactly the same thing. So if I went from one side, everything made sense. When I got to the far end, I had a negative force going down to the counter reaction. But whether things were intentional or compression changed. If I started from I went into the section that was repeated. So it's perfectly. I mean, a perfectly symmetrical one-span bridge.
So when you went into your,
are we not allowed?
So
to
we're in the
use
middle.
that?
Yeah, we're in the middle. So you got that force there. So when you got that force there,
it matched that force there.
Yeah.
But it didn't match my two horizontal. So my two diagonals.
But it's
did
symmetrical.
Not match.
It's symmetrical.
Yeah.
It must be. It has to. It's symmetrical. So if I
calculations
call that A and I call that B.
We asked around our project class.
Yeah, but if I just look at that now and I say this is symmetrical.
Certainly, it should be
the same. If that's B, well then you've made a mistake in your calculations.
But the thing is, we asked the demonstrator, and he said that there's because of some assumptions that are made that we had to make to the project that in fact because when we did the calculations, we checked the method of section checks. Like
It's
this was across all the different project groups in that class. All had the same problem and all had done 3 or 4 checks. Method of sections, method of joints. We'd gone past the symmetrical point and found that things were breaking.
That makes absolutely no
Agreed.
sense.
This is why I wanted to ask.
Yeah.
Is
Well,
there
no,
something
that
unique
makes
about it?
absolutely no sense.
Can we claim that due to those symmetrical...
No, but I don't understand how you can say they're different, because you're saying, you've calculated A and B,
Yes.
and we now get to this joint, so you're telling me this no longer equals
Because
A.
we have some point load down here, and the force, it's not like A's, the component of A going up is not half of that joint, of that force. It's some amount off of that.
Is everything... yeah, I'd have to... Have you got it here to show me?
Yeah, I can bring it up later.
Okay, show it to me after. Yes? You
okay.
emailed me. Your
I
writing's
did.
impossible to understand.
Sorry.
I can't see what's
I have a
dotted.
0 force here. So I don't...
So what's tension, what's compression? Keep on going with it. That's why I believe what you've got.
Are you sure?
No,
Like,
I don't
zero
know. That's why I have to see the pattern. So I don't even know what's in tension and what's in compression. So these are all tension.
This is compression.
Yes, tension, compression, tension.
Well, this
Keep
is
on
0.
going.
Is that...
Possible. Until I see the whole thing, I can't
okay.
comment. Yeah, so don't panic. You're not believing yourself. Yeah.
because I was like, 0, that can't be right.
Why not? Yeah, so just don't panic yet. Do the whole thing and then come back.
Okay.
Yeah? Okay. Yeah?
Right, so when we make allowance for like extra steel work and handrails and things like that, do we times the total dead load of the truss and the roof, those things added together by 1.2, or is it
Just the
the
truss.
truss? Just the truss? Okay, great, thanks.
I was doing the minimum joints for the trust. I got 700 kilometers for
You got what?
700 kilometers. That extra new one. Would that be possible
I'm not sure.
for a single? It increases as it goes to the middle.
What is it as a UDL load? You tell me what it is as a 12 per metre? Yeah, that's fine.
I was just wondering, with this method of joints, it got to halfway in the quarter way, and it's already negative 960 kilonewtons.
Yeah.
It just seems a bit excessive. Is that possible, kind of being
That's what people are saying. It seems. How do you know?
Because as soon as you get here, it's going to get to like a couple of meganewtons. It just seems... But is that what it's supposed to do?
It's possible.
Okay.
If I don't know how big your loads are,
Yeah.
but it's possible. Yeah,
Okay.
these forces are a lot bigger than this.
Yeah.
Yeah. Yeah.
Okay.
And they get bigger as you move.
Yeah.
Yeah.
Okay. And also, when we do the method of joints, don't really include the weight of the beams, do we?
Themselves.
Yeah.
You've allowed for them to be worked out.
Okay. That's what I thought. Thank you.
Okay, we'll get going. You're going to get going literally. Boy, bye. Okie dokie, let me talk to you. It says Project 1, and that shouldn't say Project 1. That should say Project 2. I'm going to tell you now about Project 2. Just because if you wish you can get going on it, I won't expect you to do anything on it until you hand Project in next week. But just now I have time, and it's in the brief to tell you about it now. The brief is on MUSO. This is an easy project, by the way. Dead easy. This is only first semester, so you haven't seen people walking around campuses with newspaper truss bridges, because you'll be those people walking around. People in second semester, I say, did you see the people in first semester walking around with them? So you are going to build a bridge out of newspaper and sticky tape only. You download the brief, and it's quite a long brief, 12 pages or something like that, and it tells you how to analyse it all, but you're not expected necessarily to analyse it. You are just to build a newspaper bridge. Now in the brief, it says it can't be heavier than 350 grams, okay? And that's a big chunky thing, and I don't want your bridges to weigh 350 grams. The lightest I've ever seen has weighed 28 grams, and I don't know if you have any idea of weights, but that's nothing. Now, when I'm saying 28 grams, it looks like one of these. So people have built things that look like this and managed to get them to weigh as little as 28 grams. And I want you to aim for that 28 grams. Okay, you are to work in your groups of 3. Hopefully you haven't murdered anyone in your group and you still all get on, and so you would stay in the same group. This bridge building is worth 5%. As far as I'm concerned, it's a gimme. I'm giving you 5%. All you have to do is meet up with your group mates over a pizza and a drink. You're going to roll up a bit of newspaper, stick it together, turn up to the lecture on the day, and we are going to test them. And you have to hand 1 sheet of paper in, and that sheet of paper has your group names on it. It has the weight of the bridge on it because they weigh them here, and a couple of sentences about what is the structural form of your truss, to which you're going to answer it's an arch, it's a truss, it's a beam, it's a whatever, and it tells you to explain the structural actions and the structural form. So it's a couple of minutes' work to fill that out. You do that, you get 5%. The bridge will be tested in week 9 in this 2-hour lecture slot. So you'll all come here, and it's going to be loud, and it's going to be hectic, and it's going to be lots of fun. Okay? Because, of course, prizes are awarded. Now, for some reason, we're not allowed to give you money. So we give you book vouchers. But you all need to buy books, or you can all stand outside the bookshop and go, hey, if you want to buy this voucher for 25 bucks, you can have it for 20, it's worth 20 bucks. It's up to you. But it is actually a lot of fun. The rig, as I said, there is a testing rig. What is so important is you read the brief to see how big your truss has to be. So, here, crap truss, okay? As you can see here, they didn't read the brief, and it's too long. So in the brief it now says, if your bridge cannot be tested because we can't fit it in the rig, that's when you lose points, okay? So we've got to be able to test it. Now, you'll see some ledges in here. Your bridge has to sit on these ledges, not down in what's the water, okay? This is considered to be a river. So the bridges have to be supported on this little ledge here. If you read the brief, you'll see the dimensions of it. The bridge has to pick up this track. The track has a certain weight. You're told the weight. You're given an idea of how much the cart weighs. There's a cart. It sits up here. We let it roll down. And if your bridge has a hump in it, it goes flying. There is a video on Moodle, so you can actually watch it being tested to see how it performs. So, as I said, this is a fun thing because we want to make it fun for you. You come in here, you get your bridge weighed, we weigh it quickly, we have the rig set up, we quickly test them. Ones that are really strong, we get an extra big weight out, a bigger cairn, we test it to see how strong they are, and then we award a $100 book voucher prize to the lightest bridge, 75 book voucher prize to the second lightest bridge, and 75 to the most innovative. So 3 in a group, we're talking 30, 25 to 33 bucks each. It's not bad, it's better than a kick in the head. What else do I have to tell you? Okay, I want you to aim for 28. 28 is very unusual, but aim for 28. If your bridge fails, you will still get the 5%. I would rather you attempt to build a light bridge that fails the test than a heavy bridge where you come along and you put it in and we all know it's going to pass. That's not to say I want every second bridge failing, but I want you to push yourself to the limits and try and get something that works. As you can see here, we have funny arch bridges, we have your standard truss bridges, we have arches above, we have all sorts of things. Now, with respect to this cables type stayed bridge, you are not allowed to stick anything to the rig itself. You have to come in, have a standalone structure that you put in, we put the deck on, we run the cart over. So, once you finish bridge 1, you have your 1 week break, then you can just work on making this thing. Okay? That's Project 2. I think I said everything I need to say about Project 2. So we're now going to go back to drawing, drawing that bending moment diagram. Before we draw this bending moment diagram, we of course need to know our reactions. We have a CY force here, AY, AX. Where am I going to take moments? Where's the best place? At A. Do people say at A? Oh, you can take it at A or at C. I'd take it at A. Taking moments of A, at A I have 20 times 4. It's going clockwise. I have CY times 8. That's going anti-clockwise. And I have 6 kilonewton, this down here, times 4, 8, 10. That's going clockwise, so that's minus. And do I have anything else that causes a moment? Yes, beautiful. I have my force 10 kilonewtons. And what's its perpendicular distance from A? Beautiful, 5 metres. Excellent. And that's going clockwise or anti-clockwise? Good. Big elephant. Excellent stuff. Okay, anti-clockwise. All of that equals 0. And from that, CY is 11.25. And I'll go to the next page here. So we can draw it here. So that is 11.25. That's 14.75. And because I have a 10 acting, that must be 10. So here are all my forces. And I want a shear force diagram from you all. So just to remind you, that's the support. That's the support. That's 4, 4, 2, and 5. Shear force bending moment diagram, deflected shape. Shear force diagram is easy enough. Start at the left, step up 614, move across. I've gone too far past the 20. I come down 20 to minus 5. I move across. My reaction's 11, takes me up to 6. I move across and then I come down to 0. Now when we come and do the vertical leg, we can look either way. It doesn't matter. As I said, we'll look at it from the left this time. So looking at it from the left, some people get confused and they want these separated out. If you want to draw them separated out, you can, but I will just draw it as one now. We are looking from the left, so we step down a value of 10 because the left side now is the top of our cantilever. We step down and then we step up because, of course, that step up comes from that horizontal reaction. So there's my shear force diagram. Now, as I said now, I could just teach someone how to do this and someone would come along and say, I'd have a positive shear force, that's a downward slope. I have a negative shear force, that's an upward slope. I have a positive shear force, I know that's a downward slope. And looking at my bending moment diagram, I have a negative shear force, that's an upward slope. So I know all the slopey directions. My shear force is constant, it's a straight line, so all my bending moments will be linear. So join the dots for me and give me some values. got enough energy. I could pick up one of these mics and go, how are you going? But you don't need anything like that to keep you awake because this is exciting enough. Okay, where's my bending moment 0? At the pin end? At the cantilever end? So I've had a couple of people come down with the project and say, this is happening, oh, I don't think it's right, or this seems too big, or this seems too small. When you do this, follow the rules first. So don't judge. Don't be judgmental of this bending moment diagram. Don't say, I think that's wrong, I think that's right. If you follow the rules, you'll get there in the end. And then you can question whether it's right or wrong. Okay, this is 0. It has to slope down. It has to be linear. And this slope here is 14.75. So that slope, that gradient, is 14.75. Now, it now slopes up. And people say to me, how do I know if it slopes up or if it slopes down? Well, this time the gradient's only 5.25. And it's the same distance over 4 metres, so it's obviously not coming up past 0. Because the gradient here now is 5.25. And this is where you panic and go, oh, I'm not sure what I'm doing. No, I know I have to come down again. My slope is downwards. So I slope down. I haven't put values on this yet. And I just join it up to 0 as I do. Going round a corner, if that's on the outside, that has to be on the outside. Because we know going around a corner, they're either both on the outside or they're both on the inside. So those two values are equal. And we know we have to end up at 0 on the top, and this is actually sloping the right way. Did you get that? Yes. Good. One person did. Oh, I'm not saying others of you didn't. I just haven't seen you nod. Okay, we need to put some values to it. The value here is just area 1, is it not? Because if V is equal to dm dx, m is equal to the integral of V, which is the area under the shear force diagram, area 1 is equal to 59 kilonewton metres. It's equal to 14.75 times 4 metres. So that value there is 57. Now I go to that next one, but I go, oh, that's too hard. It's easier to do the corner one. Because what's the moment going around the corner? I cut the corner, 5 metres. I want to know what that moment is equal to. What's that? Oops, sorry. What's this moment here equal to? Oops. Again. What's this moment here equal to? It's equal to 10 times 5, or it's equal to that area in there. So that value there is 50. So both those values are 50. Now with this third point here, that value of moment there, well, it's just A1 plus A2. And because A2 is a negative area, it would give you that value. Or I personally don't like using the area method when things get too complicated. So what I would simply do is I would cut the beam at 8 metres. It's personal preference. And calculate that value of moment based on a load of 20 and a reaction of 14. And when you do so, that moment works out to be 38. So it looks hard, but can you see I'm applying the same rules every time? And I'm using equilibrium every time. So have a think about that one and we'll move on. Okay, when I say we move on, we've actually finished that topic. So that's fine, we're meant to move on to shear. Before we do move on to shear, to bending stress, a break. Okay, well, hang on. While I'm giving you a break, I'll put one for all those people that don't want a break. Because everyone wants to, well, have a break and I'll draw something on here. And I can do project questions again.
If they use a moment applied somewhere around here, because moments don't come up on the sheet. Would that affect the opinion?
So the result of it, if you have a moment here, you see your reactions will be different. Yeah, so that's why the shape will change, but the reactions will change.
So just relying on working out the areas underneath is not.
It's good for when you don't have a moment applied. When you do have a moment applied, I just kind of go, hang on a minute, I know that I can't just rely on the so what people do is, can I write on here? When it comes to a cantilever, yeah, particularly people do that and they go sheep or I want to go up, I go down, and I go across. So then they go a positive sheep, positive down, so then they go to the moment diagonal like that because they think it starts at zero. When in fact you have to actually hit this one up because you have this moment here. So then you know the diagonal she does that. So you can rely on the area, but not just say it's that area, take away from the moment. So yeah, so when you have a moment, that's when I'm going, oh, it's too... The area method isn't then the easiest method. So when people say, how do you do the area method, I go, I don't do it that way. You can work it out yourself if you want to use that method. To me, you cut the beam. Yeah. Okay. Yes.
For the railing one, what we had is non-railing, and rather than putting it in the, we put it in 20%. Because what we did is, so what we did is rather than putting a railing, we just had two vertical and put a steel mesh.
I'm sure this is wrong with that. I got this as compression, this as depth. So what is the mixture that I'm doing right, madam? This is all compression. And then at this point I'm getting this much. And then this is symmetry, and this one I'm not getting BN equal to it. I got this at compresssion. No, this is just compressing, but it's BN is 10.
Oh, yeah. That's what it is. That's why, in terms of diagonals, I'm not sure what they're meant to.
But this one is
So what, is there a pattern? Is the compression force being less and less?
yeah. And then it's 10. But what is the
Tension.
yeah, it's getting less and less, and then again it's certain point it's being 10.
If that's what it is, that's what it is. I can't tell you whether that's right or wrong.
But what is the mistake is that this is a symmetric here.
Yeah.
So PM should be okay.
Yeah.
We are not getting it. Check
That's
it.
what someone else said.
It's 100 times check this calculation. We are not getting it.
It's symmetrical.
It's asymmetrical 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. It's symmetrical, but they're not getting PM is equal to it. We did it 100. We asked for the tutorial video also.
Yeah, they say it.
And we're not getting it.
So you've done
then this load to be negative, this load to be negative, this load to be negative. So in that case, one will be positive, one will be positive, one will be negative.
You can clearly move, but no, it has to.
But I think that they need to, but they don't get.
Yeah, I've got to think about this because now that you've told me, you're not getting it, now you've confused me. I have to think about that. I'll do that one. Ask me after the lecture.
Oh.
Yeah? Yes.
I have a problem for
Oh, deflected shape. I hadn't deflected shape. Yeah. It's all tension on the bottom. Yeah.
sorry.
It's all tension down here and it's tension here. So, from this point load, that pushes down. What? Just with this tension, it goes down. Yeah. From this one, what's it doing? Can you see what that causes it to do? I'll draw it. But, you know it's zero here, you know it's zero here. You know that load's pushing it down. According to this, you've still got tension on the bottom, so it must continue to go up. And then according to this, you've got tension on that side. Yeah? Okay, so the quick one. Okay, we'll get going again. Hang on, quick one. That's not a quick one. How that was 38. Okay, I'll go back to it. Okay. People are asking me, how did I get 38 kilonewton in here? So hopefully that's 20 times 4, take away 8 times 14.75. Are you saying that doesn't add up to 38? The other way to look at it is that area in there is 59, that area in there is minus 21, and therefore that moment there in there would be area 1, 59 minus 21, which is 38. And the second way round it, you'd say 20 times 4, considering a free body diagram, take away 14.75 minus times 8, and that I think gives you 38 as well. So that's how we got the 38. What I didn't do here, and somebody pointed out, is what's the deflected shape look like? Again, I wouldn't have attempted this deflected shape until I got my bending moment diagram, because my bending moment diagram is telling me that I have tension on the bottom throughout this beam here and tension on the outside. So in order to get that tension on the bottom and outside, I'm just going to come sideways to draw it nicely. This thing must be deflecting, and when I draw these deflected shapes, I draw them very exaggerated, of course. We're talking just a couple of millimetres of movement normally. So tension on this side, tension on the bottom throughout. So when I said in the previous problem about superposition, yes, there's a 6 kilonewton here, but it's not a big enough load to actually pull it down such that you'll get a point of inflection anywhere. So this is moving down because you have the 20 kilonewton, and because you have a horizontal 10 pushing it inwards, you're still getting that tension on the bottom throughout. So there's the deflected shape. Now, I don't think anyone had a chance to do that one. So I'm going to leave you with 2 homeworks. 2 pieces of homework, and the second piece of homework, if I can find it, the second piece of homework I would like you to do. So for this one, I want the shear force diagram and bending moment diagram, or work at home, I should say. So it's still got working. They don't call it either. What do they call it at primary school? Home learning, thank you. I'd like you to do some home learning. Learning at home. How politically correct is that? Guys, I want you to do some homework for me, please. The second one I'd like you to do is that one. It's the crank beam with a point load, with 2 point loads. Shh. Now with this one here, you can, if you want, look at superposition. So I'm just separating these out for the time being, because if you said based on that system with the 2 point loads. Lizzie, how does it deflect? I don't really know. I know the vertical force causes it to deflect like so. Hopefully you can all imagine that. And that horizontal force, we've covered, that causes it to deflect like so. But I don't know if that moment there is bigger than that moment there yet. So you can either work with this problem doing the 2 forces applied at the same time, or if you wish, you can draw the bending moment diagram separate and add them together. It's quicker to do them at the same time, but it'll be a good exercise to separate them out and to see why they are the shape they are, because of the 2 components. So jot those 2 down for your learning at home, because you've got nothing to do at home apart from learn. And before we do start on the new material, I know I spoke to my tutorial class, but I'm not sure if the other demonstrators did. Have we all got that down? Because I do want to give you enough time to write that down, so you can't say, oh, you didn't give us enough time to write it down, so I couldn't do the learning at home. Okay. Keep. We've done that one. We've done cut me. When you present next week, you are presenting not to your demonstrator, you are presenting to your whole class, and you are presenting to your whole class on the premise that they have the knowledge, they know what loading, dead loads, live loads are, they know what a method of joints is, method of sections is, they know what a truss is. However, they are in no way familiar with your particular project of building this connecting bridge. So you have to get your introduction right. You have to explain what your bridge is all about. So I would tackle the presentation in the same way you have tackled the actual task of designing a bridge. Geometry, you went out to site, you looked at the geometry of it, then you looked at the loading, then you analysed it, and then you designed it. So 8 minutes is not very long, but it is enough to actually cover it all if you are concise in what you do. Please do some practicing. Please don't meet up half an hour, 15 minutes before the actual class and go, you know what you're doing, you know what you're doing, okay, let's go in there. Because and that's what a few people do. Because as part of us assessing you, we are assessing you for teamwork. We are looking for a flowing presentation, for the same logo on all the PowerPoints. So the PowerPoints have to look like they are one. Not that, oh, person A did PowerPoint 1 to 3 and then it's obvious person 2 took over. And then you could tell where person 3 then took over. So it has to flow as one presentation. Now I have here, and again I apologise if some of you have seen this already, but Thursday, Friday people haven't. If your demonstrator attempts to show you, you can say, per Lizzie showed us in the lecture already. Here I have what I call good and not so good examples. These aren't particularly great PowerPoints. They don't have logos on them or anything. This was a project, a truss project, where they had a satellite tower to design, so a vertical structure, and their dead load comprised of the truss self-weight, and they allowed 20 kilograms per metre, and the satellite dish which sat at the top that weighed 400 kilos. And the load was conservatively applied as 4-point loads to the top of the tower. So it was a square tower. And each of those point loads added up to 21 kilonewton. Now in their case, they didn't have a live load, they had a wind load, a horizontal wind load of 1.35 kPa, and that was converted into point loads acting at each joint as you move down the tower. And the typical load was 0.68, and at the top and the bottom, because of the smaller contributing area, it was half of that, 0.34. Now I assume you all know what I'm talking about, even though you haven't seen the structure. So the first thing I want to point out is don't change your font size, and don't actually put so many words on a PowerPoint, because you guys are switching off. There's too many words up here. Now this truss was designed, and when I am talking, can you see I'm talking to the PowerPoint? What I always do is, if I put lots of words up on the PowerPoint, I actually read those words. Because if I would flash this up at you, and what are you trying to do? You're trying to read this. So if I start talking about something else while you're trying to read that, it puts you off reading it and you're trying to listen to me at the same time. So if you put words up there, read the words. Don't put as many words up there. Anyway, our truss was designed for ultimate limit state, 1.2 dead wind, and the wind was an ultimate load, and this is really boring. And you don't really know what the structure looks like. So on the next PowerPoint, I have the identical information. And straight away, you can go, okay, I know what it looks like now. So when you come and do your presentation, make sure one of the first things you have is your truss up there. So people know what you're talking about. Okay, we designed a truss tower, a satellite truss tower. I could have put dimension on this as well to say it was, 30 metres tall. We had our wind loading, which was 1.75, and we applied that as point loads at each joint. Our dead load, we applied all at the very top, and that comprised the satellite dish weight and the truss weight, and we designed it for an ultimate limit state load. Now you can see how much easier that was for you to interpret and how much easier it was for me to speak through it. So please, when you do have these overheads, visuals, pictures, as many pictures. A picture says how many stories? It tells 1,000 stories? Yeah? 1,000 words. Okay. God, you're like my daughter. She corrects me on everything I say wrong. And I say a lot wrong. Okay, so make sure you have lots of images on there. Now, there's also the wow factor. If you have time and you're good at Photoshop or whatever, you can take a photo of the site, you can superimpose the bridge on it. I don't expect that from 99% of you. But people that do it, you've got to admit it's got a wow factor to it. When my students in class see it, they all sit there and go, wow, that looks good. So, again, this is only worth 5%. It's up to you to put whatever effort in it you want, but just be aware the better your visuals are, the better your presentation starts off being anyway. Of course, you have to speak well as well. So make sure when you do put information on there, not lots of words, it can be in point form. So you can start off the presentation. We had to design a connecting footbridge between blah, blah and blah, blah. The first thing we did was go out to site and measure it. And here is our bridge. We measured these dimensions. This is what we decided our bridge would look like. Once we decided on the geometry, we then had to calculate the loading. And then just set up on your PowerPoint. Now, people don't like lots of words. If I start saying here, okay, I did a buckling analysis, and my I value that I required was 4.6 by 10 to the 6 millimetres to the 4th, I know I've lost you all. So be aware when you do that, you've lost me and you've lost everyone else in the room. We did a buckling analysis. Our buckle load was 400. From that, this is the I value we got, or based on the I value we got, this is the member size we required. So make sure you have lots of visual aids to support what you're talking about. So your audience is me never having seen the project before. Assume we know nothing about it. If you are the 6th group to present, present it fresh. Don't get up there and go, you've heard this all before and I know you're really bored and I won't bother telling you about the method of joints because you've heard it before. When you get up and present, please present. I'm going to mark you as if it's the first time I've heard a presentation. So you have to present that way. Okay. Any questions about oral presentations? Everyone in the group has to talk. Yes. You will get the same oral mark. It's too hard to distinguish between them. Everyone has to talk. If someone is absent, they won't get any of the oral mark unless they come to us with their reasoning and everything like that. But otherwise, everyone has to talk. Okay. We will get going on our next topic because it's scheduled. So, we now have these bending moment values. So what? We know how to calculate bending. We know how to calculate shear. Why did we do it? Okay? We did it because from our bending moment, we will be able to calculate a stress. When we did our truss design, we calculated a force and we effectively equated it to our yield stress. So we got our force. So in your project, you were calculating the force from your method of joints. You're saying divided by the area, that has to equal a stress, and we're going to equate that to the yield stress. So rearranging this formula, our required area will equal our force on our yield stress. And then you go in your tables and you find an area. When we look at our truss members, they had axial load in them, so our stress distribution was uniform. Now we're dealing with bending. So for trusses, there you go. Remember, for trusses, you did your Methodist joints, you calculated your forces. We now, for beams, have drawn our bending moment diagrams. From that, we find where our bending moment is maximum. And we are similarly going to look at stresses and compare against yield stress. However, our stresses now are bending stresses. And they are tension or compression bending stresses. And I have my piece of foam in, but I didn't bring it with me. When you bend something, and I've been up here ranting on about tension on the top or tension on the bottom, if I bend assume this was my ruler like so, which side is stretching the top? So that means the top is experiencing some sort of tension stresses. Which side is in compression? The bottom. That means the bottom of my beam is experiencing compression bending stresses. So thus, our stress distribution is no longer uniform. It is now triangular. So at the top, in this instance, we have compressive stresses, and at the bottom we have tensile stresses. So now we can't any longer say force on area is equal to stress. So this is no longer relevant. But there are still stresses in the system. So we in effect have to come up with a new formula, a formula that links our moment to our stress. So how do we calculate these bending stresses? We do it, I'll do it for you. Okay? But I just want to confirm with you that you understand what this stress distribution, this triangular stress distribution is. Here at the top, can you imagine it squashing the most? And as you move down the beam, in the middle of the beam or at the neutral axis of the beam, that's where you have no stresses at all. And then when you move below the neutral axis of the beam, that's where you start getting tensile stresses. So you get this linear stress distribution. So from this stress distribution at the top, I do have a net force to the left here. I call it C. And from the bottom, I have a net force to the right, T. And because of equilibrium, we know that those two forces have to add up to 0. So they are equal and opposite. And those two forces as drawn, can you see they create a couple? And that's what causes the moment in the beam. So we can imagine our strains here. So when something bends, we get stretching in the bottom, we get strains, tension and compression strains in the bottom. So we get corresponding tension and compression stresses in the bottom. So how do we calculate these stresses, and how do we calculate beam deflections, which is what we'll be doing in a couple of weeks' time? We use simple beam theory. So simple beam theory is the basis for 90% of engineering design of structures. With this theory, which I can teach you very quickly, we can very simply calculate the load carrying capacity and deflection of beams carrying lateral loads. And simple beam theory is a simplified version of a far more complicated theory of elasticity, which you'll learn in second year. Whether you do civil or mech, you'll do theory of elasticity. But we're going to just work to simple beam theory now. So who came up with this simple beam theory? It was Euler-Bernoulli beam theory, it's called as well, while Mr. Euler and Mr. Bernoulli came up with it, developed it in 1790. But as I said, one of the first engineering structures to be designed was the Eiffel Tower in 1899. So it took a long time for this information to disseminate and to be understood. I think they wrote in Latin in 1750, so boy, who can read Latin? Well, they could, but it took a long time for this theory to be understood. Now, Leonardo was interested in developing it, and so was Galileo, but they stuffed it up. They made some attempts at developing beam theory. Da Vinci lacked the knowledge of Hooke's law. When I say Hooke's law, if I write for you force is equal to kx, which is, I think, the form you're familiar with, you know when something stretches, okay, the force gets bigger. But that sort of Hooke's law theory wasn't around then. And Galileo made an incorrect assumption to start off with. So they've been trying for hundreds of years to come up with this simple beam theory, and Euler Bernoulli came up with it. So here are the assumptions. For simple beam theory to be true, it can only be applied to a member that is very long compared to its depth and width. So we're talking beams here, beams and columns. So very relevant, as I said, to the day-to-day engineering structures. The beam cross-section has to be constant along its length, so we can't have varying cross-section. The beam has to be symmetrical about the y-axis, so there's no twisting occurring. Deflections are small. So if I have my piece of string and I apply a load to it, I can't apply simple beam theory. My string isn't bending, isn't it? If I have a string and I apply a load to it, you wouldn't say the top's in compression, the bottom's in tension. You know that whole piece of string is in tension, it's stretching. So simple beam theory doesn't apply to structures that deflect a lot, or bits of rope. So deflections have to be small. The material has to be linear elastic and isotropic. It has to obey Hooke's law, and we have stress on strain is equal to Young's modulus. And finally, plane sections remain plane. That's all I'll say about that now, and we'll elaborate on that in second year. Now, as with everything in what we've been doing, these are our theoretical models. So real-life structures never meet these assumptions exactly, but they usually approximate them well enough for the theory to be fairly accurate. So in practice, many engineers forget these assumptions and often apply the theory inappropriately. But the conservative nature of structural design, however, compensates for this, and structural failures due to design error very rarely occur. So please don't think what you're doing is 100% correct. It's not. It's a good mathematical model, and it should be a conservative mathematical model. What time are we? No, we've got heaps of time. Let me get through a bit of this, and I will promise that we leave early, okay? Give me another 10 minutes. Okay, simple beam theory. What I'll do is I'll work through the proof that I have to give you, okay, and get that out of the way. So Monday will be exciting when we do some worked example. Simple beam theory involves consideration of the geometry of the beam, the type of material, and the internal equilibrium. So we use equilibrium again. So just a bit of quick revision. We know what Young's modulus is. Young's modulus is the linear elastic, well, the slope of the linear elastic region of a tensile test. So stress on strain. It measures the stiffness of the material. And we know for different materials we have different stiffnesses. What is curvature? We've come across it in bending. Curvature is the rate of change of the beam slope. Or did I define it as 1 on the radius? Yeah. I also defined it as the inverse of the radius when you try and fit a circle to the actual amount it's curving at a point. If you work out that radius there, it's the inverse of the radius. But it is the rate of change of the beam slope. So the slope at a particular point we would call dy dx. And if you look at this triangle shown in green here, dy dx is equal to tan theta. One of the assumptions is deflections are small. Simple beam theory says deflections are small. So if you all, when you go home, for some learning at home, want to get your calculator out and stick in a very small angle in radians and then tan it, you will find that tan theta is equal to theta. So for simple beam theory, we're assuming deflections are small. We are from now on going to say dy dx is actually equal to the angle theta in there. And that angle will be in radians. Oh, here I'm saying it's 1 on r. So if curvature is the rate of change of the slope, if you look at this blue line in here, this blue line represents the beam curving. And if I fit to the red line and the green line to this, they will tell me the different slopes at the particular point in the beam. So the change in slope in here, curvature is equal to the change in slope. So at Q, my slope is theta plus delta theta, and at P is just theta. So my change in slope is the change between the two angles divided by delta S, which is the distance between the 2 points. So therefore, curvature is equal to d theta ds, or delta theta ds, which in effect is d theta ds. This is just a bit of proof we have to do. Now, assuming plane sections remain plane, which was the last assumption I said, so the last simplifying assumption of simple beam theory, our shape, therefore, our deflected shape follows that of a circle. So thus, if you now look at this yellow segment in here, that's a quadrant, or that's part of a circle. So if I know the angle and I know that the length along here is ds, I can therefore define my radius here, r d theta is equal to ds. So therefore, in here, d theta ds is equal to 1 on r. And up here, we've said curvature is equal to d theta ds. So we now have a relationship between curvature and the radius of a circle. So if I have a beam here, and hang on, let me rub that out. If I have a beam here and we load it, and it doesn't deflect a lot, and I have the same beam here and we load it a lot and it deflects a lot, which beam is curving more? Well, you would say, okay, beam B is curving more. If you actually try and fit a circle to this, you'll see that circle is a lot smaller than that circle. So this beam curves more, curvature is high, the radius will be smaller. So just be aware of the relationship between curvature and radius. So we have a definition here. Now, this figure to the right here is a small part of my bending beam in here. I need to go through the proof. You won't ever have to prove it, but you need to be familiar with it. So if I work a little bit slower, you can just follow me through it and see you understand it, and then just accept the formula after that. Okay? I have a beam in here. We have the depth of the beam here. This red line here represents the neutral axis. The neutral axis of a section is where there is no stress occurring at all in the beam. And that generally, that coincides with the centroid of the circle when you just have bending in there. I fit my radius r to my circle. So at a distance y from my neutral axis, so I'm moving either down or up, in this case down from my neutral axis, I can work out what the strain is at this line down here shown in blue. Because strain is equal to change in length divided by original length. So down here, my change in length, well, if this is r, when I draw my radius now, that becomes r plus y, and that's delta theta. So this length in here would be r plus y times delta theta. So when I work out my strain, I have my change in length, there's my r plus y. Take away my original length because my neutral axis is where I have no strain, so that's my original length equal to r delta theta, divided by original length, and things all cancel out, and I have this relationship now between strain and curvature and y, which is the distance from the neutral axis. So at the neutral axis, y equals 0. So at my neutral axis, y is equal to 0, and I have no strain, which is the definition of the neutral axis. There's no strain there. Make sense? Or are you all just staring at me and your minds are elsewhere? I'm going to believe that you're with me for the ride. Okay? So here's a very important relationship to remember. Now, knowing that relationship now, strain doesn't mean a lot to us. We know the relationship between stress and strain because we're trying to come up with an equation in terms of stress and moment. So instead of strain now, we're going to change our relationship to be instead in terms of stress. Now, I, in an earlier overhead, said if I have stress in here, we know we've got a net force in that direction, and if I have tensile strain in here, we know we have a net force to the left. So if I want to know the value of the force, what will I do? I'll integrate the strain over the area. So for any section, integrating the area above or below the neutral axis gives us either the complete tension force or the total tensile force. Now these two forces, as I said, must be equal and opposite. And when you look at the relationship, how did we calculate the value of that force? Well, back here, we said force is equal to the integral of stress over dA. And for stress, we've written in this relationship up here, Young's modulus times curvature times y. So we now have an equation here. Both our forces in terms of curvature and distance from the neutral axis. So for any section, integrating the area above or below the neutral axis gives us the total forces. And of course, these two forces are equal and opposite. Where there are no axial forces applied, T plus C equals 0, since the forces in the x direction equal 0. However, because those two forces create a couple or moment, they are parallel, they're not in line. That moment is the internal bending moment. So we're now getting closer to the moment. We have the two forces that cause that moment. So how do we get from these two forces to moment? Well, if we take moments in the middle of the beam, and I know that distance there, I'll call that E, and this beam is symmetrical, I'll call that E. What's my moment equal to? It's equal to C times E plus T times E. Force times distance times force times distance. So, here, that's what we're doing. We're taking moments about this neutral axis, but we are multiplying it by our general distance y, because y represents anything from 0 down. So when we do that, we then get this wonderful relationship, which still looks a bit ugly, but we're going to work with it, which is m is equal to E, Young's modulus, times curvature, times the integral of y squared dA. And this is very important. We then define a new geometric term called second moment of area or moment of inertia. And I is equal to the integral of y squared dA, and we are going to spend a whole lecture and a whole 2-hour class learning how to calculate I. But we end up with this wonderful formula here. We're nearly there. And when we do a little bit more manipulation, we end up with a relationship between stress and moment. And that's going to be our starting point next week. We now have something linking our bending moment to stress. So we can now do some design. Bye-bye, everyone.